If you can't, like I said, 2 full stickers. As a graduate student, I can afford that. I'm Dave Worth, and I'm here to talk about cryptographic port knocking, as you know from your schedule. So first off, I need to preface my entire talk with a number of things. A1, you'll see the nice T on the schedule. It says I'm debuting a new tool today. I am. You have to download it. All the demo hardware on the planet. I brought 2 laptops from Albuquerque. One of them absolutely died today, as many people can attest to me screaming in the speaker room, and the other one doesn't run it because the dynamic libraries require 10.3. So that's exciting. So I will not be demonstrating the tool today. I'll be telling you where to get it. At the point when I get to the slide that says demonstration, here we go, I'm going to ramble on about some of the other things that I could talk about for hours on the same subject. Now, let's talk about what port knocking is before I do anything. Actually, what it isn't. This is not an attack. I've talked to a number of people who didn't read the Slashdot story, that Slashdot story, that said what port knocking is. We're not breaking into anything. It's more of a covert channels problem. So if you want to attack stuff, I'm sure 0 Day has cool stuff today. That's not me. I do have interesting things. So how many of you actually saw this article on Slashdot? Sweet, that's why you're here probably. So I started doing my research into port knocking because of this article. It was pretty exciting. I looked at it and said, that sounds cool. There are a number of problems with it, which is why it's now cryptographic port knocking and not just port knocking. And I actually started it to avoid doing my graduate analysis homework because graduate school is a nightmare and programming is lots of fun. So, seriously. So, port knocking. Define, defend, and attack. Important things. We can't even begin to discuss what cryptographic port knocking is until we actually understand what port knocking is. Originally, all port knocking is a means of passing a shared secret. In the case of in this case, it's a sequence of TCP connections to various ports in a specific order, at which point the host that receives them has seen that you've gotten N ports in a row and does something special for you. Okay? That thing that's special, generally in the original context, was opening a port in the firewall. So for example, if you happen to work in a shop that you have to use rlogin for some reason, like you use SGIs and you render a lot, like at a supercomputing center where I work, and you don't want to leave rlogin open to the world, you probably want to open it for the 5 minutes you need it and then close it. This is one means of doing so without logging in and enabling the service and turning it off. Okay, but you can do this from anywhere. So that was where the original idea came from. And of course you'll note actually, they say really neat things here that you can do this and then no one can ever tell that it's occurring. Of course no one can tell that it's occurring. It's now on Slashdot. Everyone in this room reads Slashdot. Everyone in this room now knows to look for weird TCP connections to non-open ports in a strange order and then replay them. So, let's attack the idea of port knocking. Well, like I said, it's replayable. You watch Joe Schmo put in 3 ports, 31335 through 31337, and magically a port opens on the firewall and they always SSH in or telnet in or login in. You can figure out this pattern after watching it once, let alone 10 times. We're pretty smart at correlating these things when we know we're looking at in network traffic. So we don't want replaying. And actually, the worst part is some people almost immediately started saying we should use encryption to protect ourselves in some way in these systems. And they did some interesting things. They used blowfish and an encrypted payload, which they used to then generate their port sequence. They encrypted their source IP address, the IP address that the firewall should be open to. It's not just opening the firewall. It's not like you're suddenly accepting all packets in the universe to the port we want to open, but it's a specific port for a specific IP. Right? So that node somewhere on the internet can now SSH into this machine. Okay. Well, I totally forgot to start my time. I apologize. And I will run over. So when you do this encryption, this works really well if you're on a standalone host with a nice externally routable IP address. That's not a problem. Let's say you're in a NAT. You're at a Wi-Fi hotspot, for example, or you're in your dorms, where a lot of places they just use NATs now, and you use this cool port knock. Well, now anybody else is going to be able to replay your port knock for the exact same reason that they usually would be able to, because you have to provide the external address of the NAT in the packet. Otherwise, you can't provide the unroutable address that you're actually on behind the NAT to the port knock, because sure, the firewall can now open a connection for 10.0.0.1, but you're never going to route there. So you have to provide the external address of the NAT, which is routable. And so anybody else behind the NAT can also replay that sequence of ports and still get the same service you're trying to protect in the first place. That's incredibly bogus. Now, they tried. They really did, and we all try, and I'm sure there's lots of bogosities in my code, so for saying all these horrible things about this implementation, I will pay, I'm certain. So I have to defend it. I've now told you why port knocking is a bad idea, and it can be, but it can also be good. What can it be good for? It can act as another layer in your security model to protect resources which are generally considered vulnerable, SSHD. And I say SSHD, we all trust it, we do. But how many times a year does OpenSSHD have a vulnerability that's not really a threat? Because if you're running privilege separation and if the moon is in the right quadrant of the sky, they can't exploit it. And while I believe in general you can't just exploit these things, and if you can, the skills required are very great, I don't want that. I know smart people who can do these exploits. I don't want to risk that. So any service, no matter how much we trust it, can do with another layer of security. Now a quick note, since I have time to talk about this because I have no demonstration, one of the biggest complaints in port knocking systems is as follows, and it's a very, very valid one. If you implement this port knocking system and you hide your known secure service SSHD behind it, and there's a vulnerability in your code, you've now provided a path right to the kernel, generally, or at least to user land with some privileges escalated. So now you've locked down SSH so no one can SSH to you and attack SSH, but now they can just log in by exploiting your port knocking system. This is dangerous. So when you implement it, you really need to choose your language as well and be very careful. All software has vulnerabilities that are potential. This one actually kind of raises the ante for the implementer of the port knocking system. How did I solve this problem? Now, I used Java. I wanted to use Lisp, but I'm just not proficient enough to write good Lisp code, and real Lisp hackers would mock me terribly. And I didn't want to deal with that. Real Java hackers will mock me too, but at least Java has the advantages of not being vulnerable to the same standard attacks. Java is not impervious. Nothing's impervious. If there are errors in the JVM, you can attack them. Okay? If there are errors in the JNI library I'm using, you can attack them. But Java makes the attacks harder and changes the playing ground quite a bit. There's many fewer attacks. You don't have just buffer overflows. The system throws an exception and you stop. So that's one thing you can do to start protecting yourself is choose your language as well and carefully implement. So, cryptographic techniques that I employ. I was thinking about what cryptography would actually help us. And I decided to go back to the 80s, where everyone used Telnet and RLogin and their X terminals and really insecure media. Okay, we had to have a means of transmitting passwords in plain text, or at least authentication tokens in plain view, and not be susceptible to a replay attack. To be honest, it doesn't matter whether I see your password or I see something that's equally powerful. It gives me the same rights flying across the wire. Whether it's your password or a hash of your password, if I can use it to authenticate, that's bad news. And people were well aware of this when we were still using Telnet every day before anyone decided SSH was a good idea. So they came up with something called OTP, also known as S-key, which is what you'll find in your SSH implementations. S-key is actually now a proprietary system owned by, I think, Bell Labs or somebody big, and it's in the RFC. So OTP, because the idea wasn't what was patented, made proprietary, it was the specific implementation. OTP is in the RFC version that is completely open and public. There's lots of systems that support it. MD5, how many people actually know about OTP and how one-time password systems work? Few. So I'm going to spend a little bit of time on the next slide. The resilience to replay attacks, by the way, is due to the strength, the pre-image strength of MD5 and SHA-1, meaning that if I hand you a hash, it's going to be hard for you to find something, some bit stream that you can hash to that value. Okay? So if I hand you an MD5 sum, something from your favorite file that you downloaded from BitTorrent, for example, or from Napster, it's going to be hard for you to generate another file who hashes to the same values. That's what pre-image resistance is in cryptographic hash functions. Here's how OTP works in a nutshell. We want to generate we have to generate a finite number of one-time passwords, n of them. So first thing we do is we choose a passphrase. By the way, there's a lot of details I'm not going into that are specific to the implementation that don't matter. So this is the concept behind OTP. So you choose a password and you choose how many passwords you want. We'll call 0 the initial conditions for the system. So we have a cryptographic hash function f, which we're going to iterate. So to get our first password, which we'll use last, by the way, which can be confusing, we'll just hash our password. Now to get our second password, which we'll use second to last, we just hash the output of the first hash function. So we just compose f many times. We actually do it n times to gather our passwords, and it's kind of a complicated way of converting a hash into readable words that come out of a dictionary. Again, read the RFC. It's not very hard. You can read it in about 25 minutes and get your head around how they convert it into plain text, things you can type in. You actually compute it one more time, the n+1 term, because you actually need to authenticate at some point. And the way authentication works in this system is you initialize the server that you want to authenticate to with the n+1th plain text password, or sorry, iteration of the cryptographic hash on your password. To authenticate, the server has the n+1th iteration. You hand it the nth iteration. The server applies cryptographic hash function once and compares, because that will be the n+1th term. If they're the same, it authenticates. If not, it drops you or does whatever it has to do. Okay? And you work backwards through the password list. So you start, let's say you generate 99 passwords. You'll run the hash function 100 times. You will pass the 99th password first, 98th the next time, till you get back to 1. Now, there's a lot of systems for reinitializing your passwords when you run out of passwords, and those are kind of technical details, and hopefully you won't be using these knocks so many times that you have to do that. So we understand how OTP works. Does anybody have any major questions over how that works at all? Excellent. So we can stop replay attacks, which were my major problem with the original port knocking system using this. In fact, it's designed to do so. The designers way back in the 80s said, using one-time passwords, we can prevent replay attacks. So I didn't do any new crypto, because I don't trust myself to do new crypto. I'm a math major, but I'm bad at crypto. So I'm using tried and true technologies that will take care of this problem. The nice thing about this is not only can we stop replay attacks, but we can watch them happen, prevent them, and respond to them. Okay? Because let's say I authenticate once, and there's an evil bad guy on the line, watches me authenticate once. They see my nice little plain text string pass, and they want to use it. They resend it. I've already seen this string. So I can store it in a hash table or in some data structure, and when I get another one, if I run my hash function on it and it doesn't match, I can then compare it to all the other ones I've ever had and see if it's ever been passed me before. If it's been passed me before, somebody's replaying me, and we can actually respond to that in an aggressive fashion. We watch a replay occur, and we can nmap them, we can block them with the firewall, we can run our favorite 0-day against them. You can do whatever you feel is appropriate. The latter is probably the most fun, but probably the one that's most likely to draw attention to you. So dropping them with the firewall is not a bad thought. Okay? So, I implemented a tool, cryptographic one-time knocking. You can pronounce it as you like. I pronounce it cock. It's offensive, I realize, but from what I understand from my German-speaking friends, the umlaut makes it kick. So if you want to be able to present this to your boss, you like kick. I use the umlaut to be more like Motley Crue, because I have that sense of humor. So what is kick? Kick is a Java-implemented cryptographic one-time knocking system, written in Java, because I wanted to use a high-level language that was resilient to most of the attacks, that allowed me to be a little bit more lazy with my buffer so I didn't quite have to watch out for all of you guys, and my best friend, who's a really great exploit writer. It would be very embarrassing for him to exploit my system while I'm talking to you guys about it. So I prevented that. The biggest obstacle, by the way, to installing my software is getting JPCAP built. It builds great under Linux. It builds great under Mac OS X if you have all the Java stuff installed properly. I hear it works great under Windows. I haven't tested it. Somebody will have to let me know whether my system works under Windows, because I don't have Windows. There's three major components in kick. There's the kick D. So it's the daemon. It watches for things. It listens on the wire. It does authentication. It executes the rules that need to be executed when you have successfully sent a knock. It's kind of cool. Then there's the kick tool. The kick tool is what allows you to manage knocks, build new ones, set rules up, set lists of valid IPs from which knocks can come, which is handy because not only can we watch replay attacks, but we should also be able to limit who can knock. If I'm going to be knocking from school on my home machine, someone in Zimbabwe, where I don't go to school, should not be able to knock from Zimbabwe. They should at least have to compromise the machine at my school to knock. So we can limit that. And then there's the kick knocker, the cock knocker. It's so cool to get to say cock like 60 times at Black Hat. So there's the cock knocker, and the cock knocker just generates knocks. As a side note, there are certain knocks that don't require my client. For example, I have a certain knock we'll talk about in just a moment where you can use dig, nice standard tool, to actually knock via a DNS query. That's pretty sweet, I think. So, kind of knocks I have now. You can add more. It's pretty easy. There's a few things you have to modify. It's not quite as cool in OO as it should be, but it's fairly easy to add new knocks. It took me 10 minutes to add the DNS knock after I added the first type. The type of knocks I have now, I have the OTP knock, one-time password knock. It's really simple. It's really easy to watch for. You can set up IDS rules to watch for these knocks passing you. Okay? All it is a UDP packet with the string, the plain text, human readable string, that is the one-time password in it. It took me about 2 minutes to implement the client. It was great. You can do all sorts of steganographic things. We'll talk about that in just a bit. Okay? That was just my proof of concept. The code works. I wanted the code to work before I got here so that all of you guys know that the code works. I really hate to hear people say like, oh, you could totally do this, man. Like you just have to write it yourself, but it totally works. Because they haven't done it, so how do they know? The next type is the DNS knock. The DNS knock is actually pretty cool. You choose a domain, which you're going to be knocking to. By the way, if you're running this on a DNS server, it's probably one of the domains that it's authoritative for. So I thought. And the way you knock is you construct a string, which is the human readable password, connected by underscore, since it's words and spaces, dot the knock domain. This is actually nice because it's kind of obvious if you're watching for them. You kind of know that there is no like Dorn, Michael, Johnson, Joe, Bob, dot, Microsoft.com, for example. It's probably not going to exist, but at least it kind of flies under the wire because it's still a totally legitimate DNS query. Now, the server does not have to be a DNS server for the DNS knocks to work. It can be any server on the planet as long as the cock daemon is running. If the cock daemon is running, what will happen is the packet will just get dropped and everything will be fine. Okay? If you are running on a DNS server, which by the way is what makes this covert, and the only time it really makes sense to be using these, what will happen is the cock daemon will get the packet, it will execute its rules as it should. No problem whatsoever. But the DNS server will respond, hey, that doesn't exist. And that looks like legitimate traffic. Someone watching this will say, that's a weird freaking query that just occurred. It doesn't exist. Someone typed something in wrong or copied and pasted wrong in their browser, because that's been known to happen when you highlight a block of slashdot that you're reading and then you accidentally middle click and it goes into your location. How embarrassing, because those sentences don't exist as domain names. It's perfectly conceivable that these things they're flying across are just bad data and it's not clear how they got there. I actually implemented port sequence knocks, the original thing, for completeness, because that's what everyone got off on in the first place. I suppose you could expand it in terms of the system I was describing earlier, where you actually encode a source IP that you should open for into your knocks or whatever. That's for somebody else, because I'm totally uninterested in them. I only implemented them because I thought I should. Some sort of Catholic guilt. I'm not really sure. How am I doing on time? Okay. I have 20 minutes, so, all right. So what can it do? What can it actually execute? Once a knock has been passed, what can my system do? Anything. Anything you can do on a system in a command line. Now, right now, rules are literally lists of one-line rules that are executed in funny ways, which we'll talk about in just a moment. There is no cool control flow language yet. I'm not a compiler writer. I'm not an interpreter writer. I didn't want to go through all that pain of the Lex and Bison and all that stuff. I probably should someday. If there's enough interest from you guys, I'm on it. If there's not, then it's just going to die like every other project that will someday be on SourceForge, and we don't need it. But it's where it should go. For now, what happens? You've got a list of rules, and the rules are just strings. They can contain a bunch of preprocessor macros, things that are interesting, like __ source IP and source port and destination IP and desc port, and even knockdesk, which is a little textual description of a knock, which actually, once you look at them enough, makes sense, and you actually figure out what knock is which. Okay? So those things get replaced with the actual information that belongs to them first. And then there's a few execution macros, 2 of them actually, but you could make other execution macros which are internally implemented commands. Log and print are the 2 that are there now. Print was the first iteration of log. Log now syslogs. That's kind of nice. Syslogs to the local host. Someday there'll be listeners. But this way you can actually do complete logging. That makes sense for detecting replays. Every time you get a replay, you just log it. And if you have good log analysis software, and you've been hanging out in the log analysis track, for example, and you're all over log analysis, this is handy. Because not only can you react right when the replay comes to you, but you can also respond later. So first you 0-day them, and then when you look at your logs, you realize that your backdoor is now sitting on all the servers that replayed you. So you can figure out where they are. That's kind of nice, I suppose. And after that, it's just shelled out. The string is, quickly, the parameter to the execution macro is just the rest of the line. So __ print string prints the string. Yeah. So, and then if there's no execution macro specified, it just shells it out. There's the runtime module in Java. It's basically calling sh or command.exe or whatever thing you're running on your platform. And so it can do anything you can do. Now, a quick note about this. Actually, not a quick note. We'll talk about that in just a moment. So, whoops, the important slide. Where does this fit in the context of general network security? We have 5 minutes, so this is just to wrap up, actually. Where does this fit in network security context? It's another layer. That's all it is. Systems are made up of layers, complex layers. People are always attacking systems. People find their way through every layer. That's the way it works. It sucks. That's why we're here. We're trying to figure out how to make our layers stronger and how to add more of them. Okay? This is not a solution this is one solution for a problem that has many solutions. Can you do most of what I do with this with some kind of complicated VPN where everyone knows the traffic's happening, but the code's been written in Haskell, so it's mathematically provably correct, so there are no attacks? Sure. Fine. This is a covert channel with lots of extensions. You can make it more and more covert. You can start encoding your one-time passwords in like unused header bits of TCP packets or something obscure. That's cool. Do it. Please. Actually, that'd be really awesome. This isn't a solution that's kind of general purpose. It should be used everywhere. It should be used when appropriate. The best example I can think of to date of a really cool use for it is if you have a bridge on your network. Two interfaces just passes stuff back and forth. That's this job. Let's say you actually want to manage this thing remotely. That's a pain. You usually have to walk up to the terminal, or there's some other management things for bridges, and it's kind of a pain and kind of ugly. You can have a third interface in your bridge, especially if you built it yourself, like a BSD box that bridges, that waits for a knock on one of the primary interfaces that's passing back and forth. And as soon as one of those sees the knock, it turns on a third interface, launches SSHD on it just to your host. Log in, manage, log out, unknock, close it off, and now you've managed a traditionally non-manageable or easily manageable device. So that's kind of a good example. And how much time do I have? Am I out? I'm done. Do you have any questions? 20-minute talks, they really cramp your style. What's up?
I'd like to mention that the DNS orthodox firewall or IDS.
Yep, it sure is. Yeah, Dan Kaminsky had a great talk today about DNS, so that was pretty exciting. Before I get off stage, is there anyone here who works for the federal government and has a sense of humor and liked my talk? Excellent. And this should be exciting. Thank you very much. You guys have been great.